Okay, good morning, everyone. Thank you, Kim, for the introduction. Again, I did not understand what you said, but thank you. Anyway, welcome back today. And now, today, we're going to get more into the details of these softwares of the OPUS Suite, how we use them, and why we use them as well. And my intention with these 2 days, today and tomorrow, is to make you give you an understanding of how to model, how to build up the models, how it works, and the different elements that the model consists of. And then, of course, also understand the context for the analysis, what type of results is it that we get out, what kind of questions can we answer. Okay, and I'd be very happy for any questions, either to me or through Mr. Kim, and we can discuss it together. So I really want you to help you to understand and learn. Okay, so and the setup will be a mix of some presentations. However, I really like to work within the tools, so I'm going to do that quite a lot, demonstrating on the screen how it works. I will try to do it in a good pace, but let me know if I'm too fast or too slow. But yeah, so that's the setup. And when working with OPUS Suite, we can do, for understanding, it is good to have a small model with a few data sets, a small data set, because that helps the understanding of what information we need and how to structure the data. So that's for learning and understanding purposes. But of course, the software is not built for small cases. It's built for any size of the cases. Of course, we model large systems, as we talked about yesterday too. And so I will show you some examples as well of also like bigger files with more data as well. So you get the full picture of the capabilities of the tools. Yeah, power, it's a good button. There we go. Okay, so the agenda, you also seen it in the program that was handed out already yesterday, so I'm not going to spend too much time on that. But and it's always a little bit hard to know exactly how fast we proceed in the agenda, so I'll continue working, and then when we have lunch break, we take a lunch break, and then we continue, and then we have a break in the afternoon, and so on. So I don't have any exact times here, but I try to follow the times in the printed agenda. But we start looking at the number 2, actually, because Oskar already did the first one there, the introduction to analysis-driven LCM. Oskar did that yesterday, so we dig into the model straight away. And then we'll look at the elements of a basic model, and we'll also look at logistics support optimization, cost effectiveness. We will expand the model as the day goes on, and also look at how to perform cost-effective decision support for different alternatives, situations that we might end up in. And then, tomorrow is tomorrow, so let's get back to that. Well, quite short, but briefly, why do we need the model? We talked about it yesterday as well, but analysis-driven LCM, or RAM-C, is about ensuring and maintaining the desired capability over time by providing analysis, methods, models, and tools, because we want to understand, foresee, and monitor, to be able to improve this setup. And of course, there are a lot of things that will influence the outcome in the end. But what we ultimately want to do is to make sure that we can control and understand the balance between the cost and the effectiveness of our systems. And that's the cost effectiveness. Of course, throughout the entire life cycle. We can do this, and the important here is that this is not something that you do once. It's a continuous effort to continue working with analysis. So it's a balance between, as we said, between the system effectiveness, which is the capacity to fulfill what we are trying to do. So if we want to fly, we want to be able to fly. That depends on the operational requirements, but of course there is a budget and we need to balance this. And the budget are the cost implications of the system effectiveness. Of course, we can invest in infinite amount of spare parts, but that's not going to happen because it's too expensive, so we need that balance. And the system effectiveness, I mentioned this yesterday as well, it's a combination of the technical performance of the technical system itself, as well as the availability performance, which means when can the system deliver and then what. And digging a little bit deeper here, we did this as well yesterday. It's a combination of the system properties and the support properties, given a set of operational requirements. Again, the support requirement comes from when we fly with this helicopter, there will be requirements for support, and the logistic support organization need to respond to that with the different elements that it has. And again, everything has a cost. We need a balance towards the cost. Those are the three main sort of areas of this playing field, or this world that we are trying to model and trying to analyze and understand. It's the support effectiveness, it's the reliability, availability, and maintainability properties, and also, of course, the operational requirements. Which all sums up to a cost. But this is a quite complex picture, and there are so many things that can affect this. So, yeah, it's kind of hard to keep everything in the head. So that's why we need tools and so on. And of course, there are the details here, which is the challenge. So, understanding cost, risks, competitiveness. We're talking about different types of contracts and the performance in the end. And of course, we can't just guess. We can't just take a chance and say that, well, this is good, but we should do analysis in order to get the directions where to go. And of course, this is where OPUS Suite comes into play. It fits very well, and it has been, as we also talked about yesterday, it's been developed and used for over 50 years to support this entire field, this entire playing field. So, a lot of hours of development behind this, and ideas, and consultancy works, and etc. over the decades. And yeah, this is just a very short introduction to the sort of the elements or the different parts of this suite, this software suite that we have. So we have the optimization part. We have the simulation part, we have the cost analysis, we have the evolutionary algorithm that I showed you yesterday, and then we have the integration part with Connect and visualizations with insights. So it's, but I'm not going to focus so much on different tools themselves, but rather on the functionality that we can get out of the suite. So this seminar that we're having now today is about understanding what the question is, what decisions is it that we are supporting. And I'll be presenting the concepts, going through the modeling inside the suite, and we will perform results analysis, and at the end see if we actually were able to answer the question or the decision that we had in the beginning. So that's it's built up from like a question and answer kind of setup. Question and answer. So, if we start with the first very basic one, we have we're looking at some kind of helicopter fleet here for this example. Could of course be any type of technical system. But as an example, we'll look at this helicopter, and first of all, we're going to look at the current capability for this fleet of helicopters. So we have a situation today, we have a set of helicopters that we're flying with, and we need to understand the situation today. So, yeah, that's what we're going to do. So So what all do we have to consider before we start? Well, how do we define capability? What measures of effectiveness is it that we use to define whether we are successful? Are we capable or not? What is good? And also, how do we measure performance? And how do we measure cost? What costs to include in order to actually be fair and have all the things that matters with us? And also, what elements that are required to understand and assess the capability and performance. So again, it's about the type of data we need for performing this analysis and finding those answers that we're looking at. And then at the end, most important maybe, is how we can control this and even improve, if necessary, the performance. And everyone always wants to lower the costs, so that's always an interesting question as well. So we'll be focusing again back at this picture on the performance and the cost. And this, I showed this yesterday as well, so I'll do it pretty quick, but it's just to understand what kind of information we need. If it's a simple question, if you're just looking at the capability of this helicopter, maybe it's enough to know only what's the time between maintenance, what's the time to maintain the support response time, and then we can pretty much know the availability or capability of the helicopter. That's kind of easy, but I mean, if we want more answers, we need more data and we need the analysis. So we need to break this down. So, for example, time to maintain, we need to define the tasks that we are to perform. We need to define if there are any resources. Resources, we mean like tools, equipment, personnel, other facilities where we can perform the maintenance and so on. And of course, the duration, because that's going to affect the time it takes to perform the maintenance. And then to build up or construct the support response time, there might be availabilities of the resources. Do we have any spare parts? Are there any delay times? And so on. And next level, I'm not going to go through it, but it's again, we can detail this down into the specific failure modes, into specific part numbers, and so on, and maintenance plans. Speak that one, already talked about it. So now we get into the actual first part here, which is about building our first very basic model. And the question then here again is, how effective is our current support solution for this helicopter? Yep, we'll do an analysis and try to find out. And we'll be focusing on the RAM properties of the helicopter to model that part, and then evaluate the performance and costs. So what are the basic building blocks here? I mentioned yesterday, when we build up the structure of the helicopter, we are using different concepts in this model description that we have. We have different elements of the model in OPUS Suite. And one of the basic elements is the product. So the product is sort of the family of entities that we're going to this fleet of entities. So it's the helicopter, okay? So it's a description of the helicopter. A fleet of systems might come in different shapes, in different configurations, which is described by the concept of product variants. So there are different variants of the helicopter family, okay? And then each such variant is defined through a structure of breakdown elements. A breakdown element is like I mentioned a similar thing if you have been working with LSA or databases. Often it's called logistic control numbers or something similar. So these are sort of the principal positions from a maintenance perspective. So it's a hierarchical structure that shows the different positions within the product. Okay. And breakdown elements might be of different types. So either they are of the type position, meaning that this is really just it's a place that's used as a placeholder for other parts of the model. I'll show you later to be more clear. We can also use the concept of subsystems. So a product variant might consist of a set of subsystems. Again, a subsystem is it's a hierarchical structure, so there might be children to that node. But and then the third type here is the one that we call breakdown elements of the type hardware. So hardware elements are used to place actual physical components, the one that we call the items. So items are the real things, the things that you can hold in your hand, the physical like engine or cables or whatever type of physical part it is. So again, with the going back to the LSAR, if the breakdown element was the logistic control number, the item would be the part number. So it's the physical thing that we can actually have spare parts of. We cannot have spare parts of a breakdown element because it doesn't exist. It's not a physical thing. It's just a position used to describe the structure. So that's the difference between a breakdown element and an item. So item is the physical part that we can store, that we can maintain. However, now you wonder, but why do we have those two different ones? Well, and I think that will be more and more clear during these 2 days, but it's actually a pretty good idea because this gives us a very flexible way of describing maintenance and failure modes, etc. Because a physical item can behave differently depending on where it's installed. Let's say you have, I don't know, you have the landing wheels on an aircraft, for example. Maybe they will wear out faster in the back than in the front, but maybe it's the same type of wheel. We spare them the same way, but the ones sitting in the back, they will be worn out faster because you land the rear tires first, right? So something like that. That's an example. Same thing. Maybe you have, if you have two parts of the engine, and you have one sitting on the outside, and there's one on the inside, and the one on the outside is much easier to access and replace compared to the one on the inside. So this is it's a way of being able to model complex real-world situations. And then an item can, of course, consist of sub-items. So let's say that we have, if this is the helicopter engine, an engine head of an helicopter is a quite complex component, right, consisting of lots of different sub-components. So also for items, we can build structures saying that those are childs or sub-items to the parent. And we can also give quantities. There might be 2 compressors and 4 fan parts, or I don't know, of the engine, but we can give quantities as well. And of course, also for it could be that we want to be more precise and use the breakdown element concept also for sub-items. So the model is flexible. It is constructed to be able to handle any type of situation. So there we go. We have a little bit larger system here, and we look at a set of example is some kind of engine system. We use the position type. That's why there's a P there, meaning that this is not going to be, there are no physical part at this position. There are no items related to this. However, for the rest of them, we have a set of breakdown elements. And then there is the list of items. So we use those colors of the boxes to try to be, again, we talked about visualizations yesterday, and this is trying to help our users to understand what the information that they put in the tables, and we try to represent them in a graphical format as well. And the colors means that the yellow ones, they are items, and the purple ones are the breakdown elements. And what we do is that we sum these two. So we say that each of those physical yellow items are being realized somewhere within our engine system, within the product. And then we get that combination, this picture on the right here, which is showing us which item is installed where in the product. Yes.
Just say that the structure is in line with LSA and the IPS standard. They also use this concept of
yes, exactly, with the breakdown elements. And so the concept of breakdown elements is not invented by Systecon. It's something used by the S series, and it's in the specifications. We are, as I also mentioned yesterday, we are building and developing our models in a way that make them as similar and understandable as possible for people using standards. So this is sort of a widely accepted way of describing a product. Also, product and product variants; those concepts are also taken from the standards. Okay. That was quite a lot of talking, but now I'm gonna jump into the actual software and have a look at our first, how we built our first model. Yeah, I'm not really sure how I'm gonna arrange my screens here in a way that makes it possible for you to see and me to work, but maybe like this. I'll probably do it like this instead. That's easier. And the microphone, everything in place. Okay, so right. I prepared a start file here. So how it works, really taking it from the beginning. So this is the OPUS Suite with the interface, and it works just like working in Excel or Word or something like that. That we open up Excel and then you open up an Excel file there. So this is OPUS 10, so we can open up an OPUS 10 file here. Using the open file command, you recognize this as any type of software, and we have here I have a file. It has the file ending .opi, standing for Opus Input. So I can open up this one, and we come to this model view showing us the information that we are building. So, and here on the left, this is what we call the Explorer view. I just make a quick walkthrough of the input here, the interface, so you know what I'm doing. Here is a list of input tables. I mentioned this yesterday, that this is the way that we construct the data in those tables. So, for example, going to and they're also categorized, as you see here. So I can click the plus sign. So under the product category, I have a list or a set of input tables. For example, one called breakdown element, which is the one in right here. There's also one called product, and this is where we define this family of helicopters that we are going to analyze in this scenario. So this is how you can click around to select the different tables, and there are many of them. There are different ways of jumping between the tables as well. But I'll walk you through them one by one. So it's not, that's fine. And then, of course, we can, when working with these, here we have this table that I also showed you yesterday. Here's an example. It consists of rows, and well, now it's just one row because it's just like a start file. So just by pressing the arrow down here, I can just create new rows like this, and then of course I can add any information I want and deleting it. So working here in this table views is really like working in any Excel file that you've been in. You can use the different types of commands with your keyboard that you're used to when working with Excel as well. So it's really like a standard way of working with tables. rows and columns and so on. Right? And there are many different small features that you can work with here. I can show you as we go, but I think I'll start with this one, and then I'll show you later on small tips and tricks on how to make the life with OPUS Suite easier. Anyway, what we're going to do now is that here, as you see, we're going to just arrange the size of those ones a little bit so we can read. On the left here, we see this product breakdown. As you see, the top node there is this helicopter family, which is the definition of the product. This is our helicopter fleet. It will consist of different type of variants. And in this basic introductional example, we have just one helicopter variant, so that it's one configuration of this helicopter. And to make it simple, we'll focus on just the engine subsystem here. That's why we have an S here, and you see this is also the line for the definition of the breakdown element, and it says it's a subsystem. If I rather would say that this is not a subsystem, it's actually a hardware instead. You see how it changed, so those are related. It's immediately updated in the graphical representation, depending on what data I put into the tables. So, let's go back to the subsystem there, because we want to add a couple of elements here as sub-elements to this engine system. I have a small Excel file here just for not typing everything by hand. So typically you might have this. This is the situation that I talked about yesterday with data. Somewhere you have the data, hopefully in some format, and it needs to be inputted into the model. I know, as of my experience, that very many organizations, they do have a lot of data in Excel spreadsheets. So it's a quite common situation. It might not always be organized in a way that you just can copy and paste directly, so you need to know what you're doing. You need to structure it in a way so it's easy. And that's why we talk about the standards a lot, because there you have them in an organized format that we can import directly. But unstructured data, like the one we're looking at here, is of course needs some understanding to add them. So, but anyway, I'll copy the identifiers of our breakdown elements that we want to add, and I go back to understand, and I add them here just by doing paste. And you see how the list of new breakdown elements ends up here. So BE is the abbreviation for breakdown element. I mean, you could use any type if you any type of naming convention that you like. But sometimes it's good to use some kind of prefix to the identifiers, because it makes it more easy to understand what it is. So then I know that, okay, it's the breakdown element of it. So, right. So once we've added those breakdown elements, and as you see, now we haven't given any structure here. We haven't related those new elements to the variant and the engine subsystem that we are looking at. But that's what we want to do. We want these to be sub part of the engine system. So then we need to go to another table called product breakdown. It's here. So go there, and you see here we have more of a parent-child relationship, talking about the variant and the sub-identifier and parent or mother identifier here. And this is the relation that we see at the top there, that the engine system is a sub-identifier of the helicopter variant. What we want to do now is to say that all those, the new ones that we pasted into the model are sub-elements to the engine subsystem. So I press the arrow down to get a new row, and then I paste again all the breakdown elements here that we were adding. A little bigger. Okay, and this is accurate for this a configuration of this variant that we have. We will have one, so it's easy. So I'm just gonna, what you can do here is, there are different ways, as I said, but I like to use what's called the fill down functionality. So if I mark the rest of the column like this, you can right click, and then there is a fill down option using there's also always a keyboard shortcut for everything. So it's a fill down, just similar to Excel actually, Control+D also will fill down data there. So what you saw now was that they all sort of jumped here in this graphical representation from having no parent to being part of the helicopter variant. But we wanted them to be actually below the engine subsystem. So that means that we also need, in this column here, break down mother identifier, we need to set this engine system identifier as mother. So right-clicking here, I can also select the engine system. Okay, and then what you saw now was here, you get a plus sign, so I can open it up and see how the breakdown element for the main engine part here now ended up below the engine system. Okay, so I want to do that for the rest of the elements, so I use the fill down again, so making the same thing for all those identifiers. So now we got the structure that we wanted, and click the save button. It's always, you know, it's a old habit to always save while you're working. So, okay, one more thing to do in this table is you see here is a column called quantity per mother element. So here we can give the quantities, and there's a number there. It says 1. And whenever there is a value in the table here, it means that it's a default value. So the default value of the quantity is always 1. However, I'm just going to have to take a sneak peek here. It was, so the compressor blade.
Okay.
Yes.
The resolution is not so good, so maybe if you could zoom.
Yeah, I know. That was kind of intentional. You didn't have to read. I want you to read here. But can you see this at the end of the room as well? Is it okay? Okay, great. Anyway, in the input there, better resolution now. You see here that the compressor was actually the quantity here was stated as 2. So meaning that there are 2 compressors in the engine here. Okay, so I go to that row here, it's the compressor, and I just type 2. And you see also there's a little 2 up there showing us, I don't know if you even can see that, hopefully you can. There's 2 there saying that there are 2 compressors in this element. Okay. Next step will be to add the physical hardwares here, what we call the items. So I'll collapse this one, and as you see, the next category of input tables here is the items. So go to the table called item, and this is where I define, this is a definition table, we call them that, and we define the basic identifiers. This is where they are defined, and then so it's a table where we define elements of the model. So back to the Excel file, you see that here is a list of item identifiers as well, or this could have been part numbers as well in a real world scenario. But here we use naming or letters, so it's easier for the understanding, I think. So I'll copy these identifiers, moving back to the item table here and paste. Okay. As you see, again, just as for the breakdown elements, they ended up here as not below anything else. They're just free here, so they're not added to the structure in any way. And they're also white, and that's because we haven't defined any actions on those items. So far, they're just placeholders for these items. But we can add some more information about them. For example, the description of what this is. So we can just copy this, especially this is why I show this is now it's just the same, so it's not so interesting maybe, but if we are working with part numbers, instead, then the descriptions becomes quite important. So if you're not super common to your own part numbers, it's kind of good to have a description on each of them so you know what we actually are talking about. Okay, next column in this table, it's also marked yellow, as you see up here, meaning that this is something mandatory. It's data that we need to fill out in order to be able to run the calculation later on. So we need to give prices for each of the items. This is also stated in the Excel file. So I'll copy the prices, list of prices here, and paste it into the sheet. Okay, so what do we mean with a price here? Well, this represents the cost of buying one of each of those and put them on the stock as a spare part. So this fan module here, buying one of those and putting it on the stock costs 1,700. Okay, and as you see, there are 3 digits on the value digits here as decimals. That's maybe a little bit too much. I don't want that. So I can right click. This goes for any column in this in the tool here, and I can do column format down here. And there it says. So maybe I just want 2 decimals with 2 precision 2 there. So that's something that you can change at any time for different columns. And then there are a lot of other columns as well, but those are sort of gray, meaning that they are not mandatory. We might need them to add information later on, but for now, this is what we need to give. So the name of the items and the prices. Okay, next step would be to connect those 2 concepts. So we have the hardware items and we have the breakdown elements. So these are the logical positions within the helicopter. They're just sort of see them as holes. It's a hole somewhere that we need to put something physical. Okay. So obviously we have this hardware called engine that we want to put on the breakdown element that we call engine. And we do this through a concept that is called realizations. And again, it's not a concept invented by Systicon, but it's a standard concept available in all the standards as well. So back to the products category, there is a table called product realization. So this is where we realize. It's where those logical position becomes real through one of the hardware items. Okay. So we need to connect here first of all, we only have one product variant, and it's the one that we call variant here. If we have different configurations of the helicopter, we can define different structures of those. So maybe you have a search and rescue helicopter which has some equipment that is not available on the standard configuration of the helicopters. So that's why we have this this possibility of building different variants of the product. Okay, and then we said that for the breakdown element called engine, selected here, we'll do one by one first. We want to realize this element with the hardware called engine. So in the item identifier column here, we select engine. Now I saw here how the node in the tree for the engine, it jumped up from the list of available items up to the breakdown element engine here. And this sort of layer on layer is used, it's a way of trying to represent this realization that we just modeled sort of on top of each other, showing that the hardware item is installed at this position. Of course, we want to do the same thing for the rest of those items and breakdown elements. So I'm a little bit lazy, so I'm going to copy. So I go back to the breakdown element table. We did the engine, but then I'll copy the rest of the list here. Copying and going back to the product realization table here. And I'll paste those breakdown element identifiers in the list. And then I do the same thing for the items. So I go to the item table. There we go. And we have the engine already. So I'll copy the rest of the list. copy, and then going back to the product realization table, and I'll paste them as item identifiers here. Okay, and then you wonder, well, they're still here. Why are they not moving up to their represented breakdown elements? Well, it's because the data is not complete yet. I haven't filled out the helicopter variant here in the first column. And since I have a pretty small screen, I've selected to hide what we call the log window. But there is actually something under the view command here, there's something called a log. If I just open it for a while, you see here how we get some help when we're building up the model, showing us that in the product realization table, this record is ignored because the product variant is not defined. I understand if it's kind of hard to read at the back, but that's what it says. So there is a record ignored due to there is no product variant. So of course, I'll close this. It was just to show you that you get some help here. Also, I can scroll down a little bit. I'll read for you because it's so small, but it also says in the table product breakdown, we have a problem, and it's that we have a product element of type hardware that has not been realized. And it's the, for example, here it's the fan, and that's also why it's red here, as you see, also showing you that there's something missing. So we're trying to help the users to guide them through this building of the model, looking at these different steps. So yep, I'll remove the log here just to get some more space on the screen. So what I need to do is, of course, to define this, our single variant for all those realizations. So I use this fill down functionality that I talked about again. And now you see how all the items jump up here and become realizations for those breakdown elements. Okay, so that was sort of, oh yeah, right, there's one thing left, I forgot. In this category of items, there's also something called component group. So this is a sort of a concept where we can, that makes it more simple to model, because if you have a real world model with very many items, and you need to give data for each of them at many, but it's the same data maybe for all items, it will be very many rows in your tables quickly, and it might become complicated to build the models. So then we have this concept of groups. So we both have, now we look at these component groups, and it can be groups of breakdown elements or groups of items and etc. So here we have one that we call variant and one that we call items. So the variant for now, was pre-filled here, but the variant consists only of one identifier, which is the helicopter variant, because we only have one variant, right? But let's say that we have 5 different variants, and then we want to refer to them in some other table with similar data, then we can create a group of those. And that might be good for the items. So I'm going to use this group that was already defined. It's called items. Now create a group of all the item identifiers. So back to the item table, here where we have all the identifiers. I will mark the list with all of them, and I do copy, Control C, or yeah, you know how to copy things, I guess. Right click and copy, or Control C. And going back to the component group content. So what's the content of this group? So, and I'll paste here. So right click and paste, or yeah, again, Control V. I tend to use quite a lot of shortcuts, so I'll also try to make myself explain as well. Fill down, remember, I use Control D, but it's here, fill down, just a quick way of giving the same value for all those. The rest of the rows. So what happened now was that we created a group that we call items that we can use to refer to this group, and we want to refer to all the item identifiers. Okay. So that concludes actually the first part of this demonstration of how to building the first model. So we've built up the product breakdown. It looks good here. We have no red boxes. And if I bring up that log window again, just to make sure, as you see here, there are no errors or warnings of any kind, meaning that it looks good. We're not missing any information in that part. But there are, of course, some more parts of the model that we need to continue building on. Let's get back to the presentation. Okay, and continue. So when we talked about the product and how to build up the product, but next part is to talk about the events. These blocks of elements is also it relates to the ones that I showed you yesterday when I did this very first introduction of the data that we need for an OPUS Suite model. Maybe you remember, it was product was one of them. That was the first one. Now we look at events. And the events is a way of describing what happens to the systems when we start to operate it. So what happens when we start to fly with a helicopter? And typically, the basic one is what we call failures. Those are random events, meaning that it's not a planned event. We don't know exactly when it happens in time. So there is a distribution behind this. And for optimization, without being too technical, it's a Poisson process. Okay, so we have exponentially distribution of the times between each event. That's classic assumption from the mathematics for these kind of problems. Anyway, those are defined as failures. So that's what we call a failure. They can be defined, typically they are per operating hours. So if we operate on average 100 hours, then we have another event of this type. So again, that parameter is going to act as an input to the statistical distribution. Okay. But it can also be other types rather than only operating hours, and it can be calendar hours. I guess you understand the difference. Well, if we fly 200 hours per year with a helicopter, those are the operating hours. But there are actually much more calendar hours in 1 year. So it will affect how often this failure happens. And it depends on how, again, this is because how do you have your data? What kind of data do you have? So this is a way of supporting the users in inputting data in a format that fits the sources of the data. You can also represent the failures per kilometer. If we're driving with a land vehicle, maybe those steel pads on the tracks that I talked about yesterday might be more representable by a number of failures per kilometer instead. Or if we're talking about engines, often we can talk about engine cycles. If it's a weapon system, it can be the number of firings. If it's an aircraft, it's the number of landings and takeoffs, etc., etc. So it's flexible and you can define it, but the most common one and commonly used is the number of operating hours. Okay, so a failure can be assigned to either a breakdown element. And if we do that, it means that, as we saw before, we can a breakdown element can have different realizations in different configurations. So that means that if we define the failure for the breakdown element, it will always happen on that position, no matter what hardware that is installed. Or we can assign a failure to an item, to the hardware. If we do that, it means that this failure is accurate for this item, no matter in what configuration it is installed. And then the third option, of course, is to add it to a combination of a breakdown element and an item. It means that this failure only happens for this item when it is installed at this location. Again, this is also a a replication of how this is represented in the standards. So failures can be represented in this way. It's a flexible way of doing it. Gives you a lot of options. And also a failure in some, I know, maybe a bit old, not in the new standards or the new specifications, but in older ones we often talked about failure modes rather than failures, but it's ultimately the same thing. So you can have multiple failure or failure modes on one and the same component, right? So it might be that it wears out, or you crash, or whatever it might be. But you know this from when you're doing reliability studies, that you can have multiple failure modes on one and the same component, and that's also possible to represent in the model here. Okay, the other part of the event section, if the failures are the random events, then we have what we call preventive maintenance. Those are scheduled events. So those are the ones prescribed in your maintenance plans, saying that every 500 operating or flight hour, we need to stop and we need to do X, Y, Z. Okay? It can also be, again, defined by the other kind of measures like kilometers, engine cycles, etc. But the important part is that this is not a randomly distributed event. It is a planned event that we know when it happens in time. So quite different in its shape. And it works just as for the random events, how we assign them. We can assign them to vector elements, item, or combination. And I like this picture, actually. So this shows us what happens more in detail when we talk about the event. So at the left here, we have our system in operation. So we can fly with a helicopter. Then something happens. There is an event, and it can be either a failure or a PM, right? But if it's a failure, we need to repair it, because when the event happens, the system becomes unoperable. We have to stop it. We can't fly again. We have to go back and land and fix this failure that happened. But once we've repaired it, to be able to repair it, we need to perform some kind of maintenance. And that goes for PM as well. It doesn't matter what type of event. But for the PM, we have a PM schedule telling us what type of activity that we need, or measures that we need to take in order to make the system operable again. Okay, so the maintenance helps us to do that. So once we perform the maintenance, then when it's finished, we can go back into operation again. And those are also the concepts that we use in the model. So we have the failures that we define, and then we define what the repair that's needed, and that's some kind of maintenance, and then we can operate again. So how do we describe maintenance? Well, it's all based on tasks, the concept of task, as you see at the bottom. So a task is simply something, it's a maintenance action to take. It can be typically it's some kind of repair that you do. And it has a time, it has a turnaround time or a duration to perform the task. It might also come with a cost. There's a cost associated with performing the task. And you can, of course, also connect any type of resources that's needed to perform the tasks. Again, a resource is the tools or some documentation or a facility or personnel, an engineer or whatever you might need. So, and then when we describe the task, that's sometimes it's just one task that is needed to be performed in order to fix the helicopter or the system. But it can also be a list of things to do. And working with LSARs and so on, you're probably used to see a list of things that we need to do to fix the item. And then that's what we call a task package. So we can describe this as a package of tasks. But tasks are always the smallest building block here. So we start with the tasks and then we can group them together into a task package. And when we talk about preventive maintenance or scheduled maintenance, maintenance plans often consist of actions on multiple components. So every 1,000 flight hours we need to do X, Y, and Z, and that might be activities performed on different components. And in that case, we use the concept of maintenance activities. So maintenance activity can group together either tasks or task packages for multiple elements or components. Okay, now that was an introduction to the events and the maintenance. So let's add this to the model. For unit what? I think 1 hour at a time listening to me is pretty good. So should we take let's say 5 to 10 minutes break, and then we continue. Okay, great.